Hello and welcome to my talk about hitting long-directed cycles is fixed parameter tractable. My name is Alexander Göke, and this is joint work with Dániel Marx and Matthias Mnich. In this talk, I'm going to consider the directed long cycle hitting set problem. An instance of the directed long cycle hitting set problem consists of a directed graph G and two integers, k and l. The task is to find a set S of size at most k of the vertices, such that after deletion of this set S, every cycle in the remaining graph has length at most L, or to decide that no such set exists. Below, you find an example of such an instance as a directed graph, and we set the size of our solution set to be at most 2 vertices, and we want to hit all cycles that have length more than 3. An example solution for this is marked by the red vertices, and you can see that after the deletion of those 2 vertices, there are remaining cycles in our directed graph, directed cycles, but they have length at most 3. For this problem, we want to find fixed parameter tractable algorithms that are algorithms that run in time f of k and l, so our parameters, some function of our parameters that is independent of the input size, times a polynomial in our input size, so the number of vertices n, but this polynomial is independent of our parameters k and l. And there have already been some special cases which were considered. The first special case is feedback vertex set, so the undirected version where you're given an undirected graph and are asked to delete at most k vertices such that there are no cycles left, so it becomes forced. And this is a special case of long cycle hitting set as I presented it to you before for L equals 2. You can see that by replacing each undirected edge by 2 directed arcs in opposite directions, and all new cycles you insert in this way have length 2, and by setting L equals 2 you ignore them, and every original cycle has length at least 3, and these you want to delete, and this is why L equals 2 suffices. This problem has been shown to be fixed parameter tractable by Downey and fellows in 1995. And the first algorithm, which exhibits a runtime of 2 to the O of k, was given by Gu et al. In 2006. There have also been improvements over this in terms of the base exponent or the polynomial running time, but I won't consider them here. Then there's, of course, the directed feedback vertex set problem, where you're given a directed graph and want to delete at most k vertices, such that it becomes acyclic. And this is the special case of long cycle hitting set for L equals 1, as every cycle in a directed graph without self-loops has length at least 2. So you hit all those cycles by setting L equal to 1. And it was a major breakthrough that this problem is indeed fixed parameter tractable, as shown by Chen et al. In 2008. Based on these 2 results, there has also been work on the so-called feedback vertex set problem in mixed graphs, where your input is a mixed graph, that is a graph that has undirected edges and directed arcs, and a cycle can use undirected edges and directed arcs, but only in the right direction. And by doing the same reduction as in the feedback vertex set case, that is replacing undirected edges by opposite directed arcs, we can see that this is a special case of long cycle hitting set for L equals 2. And this problem was shown to be fixed parameter tractable by Bonsma and Lokstanov in 2011. So we add to these results by showing that directed long cycle hitting set is indeed fixed parameter tractable in the parameters k and l. We also show that unless p equals np, there is no FPT algorithm in either only parameter k or only parameter l, as the case where you don't want to delete vertices but only check if it is a solution, you have to detect whether there is a cycle of length longer than L. And in the special case of n equals 1, this is the Hamiltonian cycle problem, which is NP-hard. And in the case where you fix L equals 1, we have seen this is the directed feedback vertex set problem, which is also NP-hard. To design our algorithm for a long cycle hitting set, we take a look at the algorithm for directed feedback vertex set due to Chen et al. As a short reminder, what is the directed feedback vertex set problem? As I already told you, you are given a directed graph and an integer k. And we want to find a set of vertices of size at most k, such that after the removal, the graph becomes acyclic, or we decide that no such set exists. Again, this is the special case of long cycle hitting set for L equals 1. Here you can see an example graph, directed graph, and we want to delete at most 2 vertices such that it becomes acyclic. And the red vertices form a solution to this problem. As you can see, after removal, the underlying undirected graph is a path, and therefore there are also no directed cycles in this graph. So now let's take a closer look at the algorithm by Chen et al. They mainly do 3 steps in their algorithm, which are 3 reductions. The first major reduction is to using disjoint iterative compression, and we are left with the so-called disjoint feedback vertex set compression problem, which suffices to consider that it will solve you iteratively the original problem. And in contrast to the feedback vertex set problem, you are additionally given a vertex set T of size at most k plus 1, such that G minus T is acyclic. So T is a solution of size 1 too big, and you want to find a disjoint solution, so set S disjoint of T of size at most k, such that G minus S is acyclic, or decide that no such set exists. So we are looking for a disjoint solution, that's why it's called disjoint, and for a solution that is smaller, that's where the compression comes from. And if we consider this problem, we have the advantage of already having a solution T. Now we want to get some properties of this solution T. For this, in a second step, we fix an unknown solution S. And for any solution S, we know that G minus S is acyclic. That is, there is a topological ordering of the vertices of G minus S. As, for a picture, there is an ordering of the vertices from left to right, such that also the arcs only run from left to right. You can see here. And then in green, I marked the vertices of T. And you see that this topological ordering also defines an ordering on the vertices of T. And now, as we have only boundedly many vertices in T, k plus 1 many, we can guess an order T1, T2 to Tk plus 1, in which the vertices appear in this topological ordering of G minus S. We don't fix ourselves, or we fixed an unknown solution, but we don't have to know that solution to get the ordering, as we guess all orderings on the vertices of T. If we now fix this ordering of T, we come to a third step, which is called skewed separator. And for this, we again look at T, which is a solution that is every cycle intersects T. And now any feasible solution that is disjoint from T has also to hit the cycles. And every cycle must go to T, so it has a Ti to Tj path in them. And by the way we guessed our order of the Ti's, we know that that the solution must intersect all Tj Ti paths for j lower or equal to I. So in the example, there may be no path from T3 to T1, as this would violate our topological ordering of the vertices of T. And there may also be no self-loop, as in the example T4 to T4, as every vertex is in its own directed connected component, strongly connected component. as you have seen before. And this problem of hitting those tj, ti paths for j lower or equal to I can be solved by the so-called skewed separator problem, which also Chen et al. Gave an algorithm for in their work. And now we want to take this three-step approach and apply it to directed long cycle hitting set. So for the first step, we are also trying to do disjoint iterative compression. And it turns out it works. So we can assume that we are additionally given a vertex set T of size at most k+1, such that every cycle after the deletion of this vertex set T has length at most L. And we now are searching for a set vertex set S disjoint from T of size at most k, such that every cycle of G minus S has length at most L, or decide that no such set exists. Now we move on to the second step. Remember, we wanted to guess an ordering of T corresponding to the topological ordering of G minus S. Again, we fix an unknown solution S, and now we already have a problem, as G minus S may not be acyclic, and that's why we don't have a topological ordering of G minus S anymore. However, we have a topological ordering of the strongly connected components of G minus S. But in a single such strongly connected component, there may be several vertices of T. Our main idea now is to find a closed walk connecting these vertices of T, say T and T prime. Such a walk must exist since they are in the same strong component of G minus S. And our idea is to guess such closed walks avoiding S and contract them. And for this, we make use of a tool we call K-representative set of paths. A K-representative set of paths is simply a set of paths with fixed endpoints, here T and T prime. And we want the set to have the property that for every vertex set of size at most k, if we delete such a set X, that if there's still a T to T prime path in G minus X, we already have such a path in our set P. Of course, we are searching for a possible small set P, such that a small number of paths we can guess on or do other operations that represent the connections in T from T to T prime, avoiding sets of size at most k. And now we have this lemma for strongly connected graphs where every cycle has length at most L. Just think of the strong components of G minus S. And then for every pair of vertices in them, there is a K-representative set of paths of size, some function of L and K, times log n. And we can find such sets in essentially the same running time. And now this allows us to guess those closed walks, which are paths in both directions, connecting these T's, but avoiding our solution set S, which has size at most k, and then contract them. Of course, for contracting them, we need another combinatorial lemma, but we also show that, so we can contract those closed walks in a same strongly connected component to a single vertex of T. And now every strongly connected component contains at most one vertex of T, which is our solution S isolates them somehow. And we can guess an order on those vertices of T in the connected components of G minus S. So now we have something like the ordering in for the S-cyclic case or the directed feedback vertex case. In the third step, we now want to do something analogous to the skewed separator problem. That is, we want to find a set S such that there is no backward path, so a tj to ti path for I lower than j. That would be a T3 to T1 path in the picture below. Against the existence of such a path would violate the guess of our topological ordering before, as only a single vertex may lie in each strong component of G minus S. But for the self path, so a Ti-Ti path or a T4 path in the picture below, we don't get rid of all of them because there may be cycles left as long as they are not too long, that is not longer than L. So we only want to hit long Ti-Ti path. Now the main problem is that skewed separator applied to this would also hit the short Ti-Ti paths. So we have to construct another algorithm using structure of graphs with only small cycles in it, so how G minus T looks like, to get an analogon of skewed separator for this case. But it can be done. So a short overview of our algorithm. We first do disjoint iterative compression as for directed feedback vertex set, and it just works. In a second step, we reduce to isolating long cycle hitting set. That is a long cycle hitting set that isolates every vertex of T in its own strongly connected component, so no other vertex of T is present there. And for this, we develop the useful tool of K-representative set of paths, which may be of independent interest, to find a short, small set representing all connections, avoiding a small deletion set. And then we use it to find and contract closed walks in G minus S, connecting our vertices, so we really get one vertex per strongly connected component. And in a third step, we derive an analog of skewed separator for our length-bounded separator problem, which requires really more technical work, and I won't go into any details here. As a conclusion, we showed that directed long cycle hitting set is fixed parameter tractable in parameters K and L. We also showed that a single parameter of these won't suffice. And our main open question really is whether we can find an FPT algorithm that has a good asymptotic runtime when we fix either K or L. So if we fix L, we want a runtime of 2 to the O of K log K times poly n, matching the runtime for directed feedback vertex set. And also interesting is if we fix K, then we hope for an algorithm of 2 to the O of L times poly n, which is essentially the runtime required to verify the solution of our directed long cycle hitting set problem.